for it. Sweet. Today's topic is Go concurrency. And this is probably one of like two things in Go for me personally that makes me choose Go in a lot of circumstances. If Go did not have the concurrency story, the concurrency primitives, the features that it gives us today, I likely would not choose Go for a lot of the projects that I choose. So this is one of my favorite aspects of Go. And I'm hoping that we can start with some of the theory and then go through some examples and see how to use, try and use concurrency properly in Go. So first off, let's talk about how Go's concurrency actually works. So Go uses what's called an MN scheduler. That means that it schedules virtual threads on top of OS threads. So if you want concurrency, at the very bottom, you have to have OS threads. OS threads are what let you execute logic on different cores of your CPU at the exact same time. One of the big problems with just using OS threads, which many languages let you do, like Rust is a good example, and like the OGs, right, C++, let you work directly with the OS threads. One of the problems with that is OS threads are often heavier than virtual threads. And so to kind of put some hard, oh yeah.
Real quick, the screen you're sharing is black.
Oh, thank you. Hang on. Let me see if I can reconnect it.
Yeah, I was about to, I just left to rejoin to see if it was me.
No, it's not you. My whole system's having a conniption this morning. Yeah, sorry, I'm also having a conniption this morning. I've got this cold that I just can't get past. All right, I'm gonna stop OBS for a second, see if we can start fresh. Okay, let me try connecting directly to my computer. I'm going to, sorry guys, I'm just going to restart my computer real quick. And if we can't get this to work, then I'll try something else. But give me 2 minutes.
In the meantime, if anyone would love to share any information about like the Go projects anyone else is working on, we would love to. We're looking for other code bases to study and learn from, particularly within the Adobe ecosystem, because, you know, maybe it has to do with ethos or something like that.
So I think the one that's, I don't know if Clark has told you about it, the one that's most kind of advanced is, I don't know if you're familiar with Hubble. Is that?
Yeah, we've spoken about it a bit. Yeah.
Yeah. Okay.
But Brian doesn't know.
So with Hubble, the part that's developed primarily in Go is the update management side of things. So Hubble is like its own binary. There's like a functional side to it, but then one of the problems that we had was just distribution, just getting it across the fleet and getting it to a point where like the distribution of versions across all of Adobe was a little bit more homogeneous. We had a spread from Hubble 3 all the way up to Hubble 4.6, and like getting a new version out just meant a ton of work for everybody. So we needed a way to manage updates remotely if possible. And because that's a kind of a big job, there are anywhere between 200 and 400,000 posts in Adobe at any one time. So like synchronizing across all of that was a specific problem set that Go was kind of uniquely suited for because of the ease of using gRPC with it. And yeah, it just made sense because we started both the management platform side and the local kind of local to the host side part of the code base about at the same time. And we knew we'd hit roadblocks with Python because you have to wrap the whole environment in the binary, and it can be pretty memory intensive, and we didn't want to increase the amount of resources that we use up from the hosts almost at all, because that's always a concern with like agents that are mandatory and people are told they need to install. So yeah, it's really been a big help, and Clark's been pretty central to that. So yeah, we're all here to learn from him.
I see. Looks like he's back on. I see some content.
Hey, you guys see my screen now?
I see a slide, yeah.
Yes.
Sweet. Okay. All right. I'm sorry about that. Restarting it solved the problem. Did I interrupt a conversation?
No. It was perfect
Okay.
timing.
And I'm just filling in and trying to sell Go for you. So.
And thank you.
Wait, thanks, Merch. I appreciate that. Okay, so what I was talking about was why I was trying to make the distinction of why would we want virtual threads over OS threads? Because Go uses virtual threads, other languages allow you to use OS threads. What's the difference? Well, one of the reasons is that OS threads are just generally more expensive. So for example, last I checked, Windows OS threads allocate minimum 1 megabyte of stack space just to create the thread. Whereas Go routines allocate around 8 kilobytes. And I think that number actually may be outdated. I think it might be a little smaller. But last I checked, it was about 8 kilobytes. And so what you'll see in kind of the Go world is the team actively encourages people to spin up hundreds of thousands or millions of Go routines because they're so cheap. And so in a large server, say like an API server or like a gRPC server or something, what will happen is every TCP connection that comes in, like normally you would actually just hand that connection to its own Go routine and just say, run with it and deal with the connection. And so large numbers of Go routines are encouraged in Go because they're so inexpensive to make. Now, how does that work when you have, 1 million Go routines, but say you only have like an 8-core machine? And that's where this MN scheduler that I alluded to a minute ago comes into play. The idea is you map M Go routines onto N OS threads. And so if you have a million Go routines, you figure out the most efficient way to schedule those onto the OS thread. And usually the way you do that is Go has some built-in smarts, I guess you could say, that let it know when a Go routine is waiting for something, when it has nothing that it can do. And it will actually remove the execution off of the OS thread and replace a different Go routine that can make progress in its place. So to kind of put some more concrete terms to that, say you're making an HTTP request, like an API request or something in Go. you're going to have some work involved on your side, on your CPU, actually creating the request, serializing it to JSON, opening a TCP socket. And then once you write to the TCP socket and that's gone, then you're just waiting for the response to come back. And so under the hood, the Go scheduler might say, all right, this Go routine that just fired off its HTTP request is just sitting here waiting. So I'm going to remove it from an OS thread, and I've got this other Go routine over here that can make progress. So I'll kind of swap them around. Any questions on that, like high level idea before we move on? Okay. So this model has a couple implications. And one of them is that it scales very well for IO bound problems and not very well for compute bound problems. So say, for example, you wanted to just compute, a bunch of large prime numbers and, sequentially. So you're just going to be computing prime numbers. And let's say that you have 8 cores to do that. Oops. 8. Oh my goodness. My snap. Yeah, there we go. You have 8 cores to compute those large prime numbers. Throwing a million Go routines at that problem is not going to get you any faster than throwing 8 Go routines at that problem, because you are dealing with a problem that is compute bound, meaning the only progress that can be made can only be made when you actually have it executing on your CPU, which is not the case for an IO bound problem, where half the problem is just waiting for something to come back, a network request, reading the contents from a file, those where you're actually waiting for like the data to be paged off the disk. Those sorts of problems, you do get benefits of having more Go routines and CPU cores. And so what I've kind of tried to illustrate in this graph is that for compute bound problems, as the number of Go routines increases on the bottom, your performance decreases right here after you pass the number of CPU cores. And the reason that it decreases rather than just like plateaus is because the MN scheduler does some scheduling, right? It's context switching, essentially. It's saying, all right, Go routine number, 500,000, you've been working for a while, so I'm going to swap you out with somebody else who needs to also do some work. And so you kind of get to this point where compute bound problems perform worse with lots of Go routines because the scheduler is spending so much time context switching between problems that really just need to be on the OS thread the entire time. For IO bound, that's not the case. You're obviously going to have some cost to context switching. So that's kind of why I've showed some sort of a parabola or some sort of a plateau here. But generally speaking, IO bound problems scale extremely well on an MN scheduler like the one that Go has. The reason that I share this is there was probably a temptation for me to, like, once I had first learned about Go routines, to like throw them at everything. Like, man, I'm going to speed up this addition and the subtraction. And the reality is that there's not a lot of wins there for compute bound problems beyond a certain point. So IO bound is kind of where Go MN scheduler really shines. Any questions about that? Okay. Let's go ahead and look at some code. So I'm going to go ahead, I'm going to show you one thing. So before we kind of jump into the concurrency stuff. So I had mentioned a couple weeks ago that functions are first class values in Go. And we need this kind of context so that you'll understand the code that we're about to write. So for example, that means that you can create a function and actually assign it to a variable. And then later on, you can execute that variable, which is holding a function like this. One of the things that you'll see in Go is an actual anonymous function that is immediately executed. What I mean by that is if we just remove the assignment to the variable and then move the function call right after the function definition, this is a piece of code, a code block that will execute immediately because I'm not putting it into a variable anymore, and then I'm calling it right at the end. So this syntax might look a little bit weird. I just want to communicate that this is the exact same as this. And we'll see why that's some important context in just a second. Any questions on that? Okay. So I'm going to whip up a basic example that we'll use to kind of work through some concurrency ideas. All I've got here is a counter that we increment over 1,000 times, and then we print it out at the end. So as expected, well, not quite as expected. There we go. We get our 1,000 at the end. Now, when we want to make a section of code concurrent, like in Go, when we want to run it at the same time as something else, we can do that with the Go keyword. And the Go keyword takes one parameter, and that is, oh, sorry, it just takes one thing after it, and that's the function that you want to run concurrently. So what you'll see a lot of times is that someone may go like this, declare a function somewhere, and then run foobar concurrently. Totally acceptable, happens all the time, especially when you want to run, a big section of code or whatever. You may also see something like this, where they declare an anonymous function and immediately dispatch it to run concurrently in Go, like this. So now this code, what happens between these two braces runs concurrently with anything else that happens to be running. So in essence, what we're really doing here is we're looping 1,000 times. We're creating 1,000 Go routines that increment a counter one time, and then we're printing that out at the end. Now, we'll see some kind of interesting results here. If I run this a couple times, you'll see that the number's actually different each time. And it's not 1,000, it's less than 1,000. So what's kind of the problem here? Well, there's a couple principles I think to take away. One is that in Go, the program does not wait for all of the Go routines to finish executing before the program exits. When you get to the end of your main function here, anything that's still executing in separate Go routines, which would be denoted by this M1 and M2, is terminated along with the rest of the program. In other words, if we go back to our code here, when we get to line 12 and we execute that and the main function returns, program's gone. So what that means is that at least one of the problems is we have no guarantee that all 1,000 of these Go routines have finished doing their incrementation before the program executes. So we need a way to make sure that all Go routines finish before we actually return from the main function. Any questions there?
I think I have a hard time understanding that because the for loop is technically still executing and the counter's in the for loop. So shouldn't the for loop finish because it's not done iterating?
Yeah, good question. So that would be true. Your assumption would be true if we were not running this Go routine. But what happens when we actually wrap this counter plus plus in this Go routine, we're going to basically take this function and we're going to hand it to the Go runtime, to that MN scheduler, and say, I need you to figure out how to execute this on your own time. And I'm actually going to proceed and just do what I'm doing. That's what it means to actually do this concurrent programming. Is I want this piece of work to not block my ability to proceed. If we didn't have this, this counter plus plus would do exactly what you said. It would block our ability to proceed until it's done. And that's one of the reasons that we saw the full 1,000 printed out. But in this case, we're saying, you figure out how to get it done. I'm not going to wait for you to do it. Just figure out how to get it done. Does that answer your question?
It does. That's interesting. Thank you.
So
yeah, no, yeah, go ahead, Murcha.
So is the Go keyword what triggers the Go routine, or just the fact that we define this anonymous, I guess, function? Like, could you just say Go counter plus plus? Would that do anything?
It would not. So let me show you kind of what the distinction is. So if I do it without the Go thing, it works just fine. So we've declared an anonymous function, which is effectively no different than this. We've just done it in an anonymous function here, and it runs synchronously. We're not using the Go keyword. We're not handing this function over to the Go runtime saying, hey, go execute this on your own time. We're just doing it right here. It's the Go keyword prefixed in front of a function that says, hey, Go runtime, take the following function that I'm going to give you. In this case, it's anonymous, but it could be, an actual function call as well. Go take this Go function and find a time to run it on your own. You could not do, to follow up on another point you made, you could not do something like this just because there's no function here. And so if you wanted to effectively do this, where you're just saying, I only want to counter plus plus, you have to put it into a function that executes immediately, and then prefix that with Go. Does that answer your question, Murcha?
Yes, it does, but I do have a follow-up. Is the fact that you declared counter outside of the function declaration any kind of concern? Like, is there a context issue here? Do the coroutines alter the same object? What's the story there?
That's an excellent question. And we'll kind of see some interesting implications of that question in a minute. Moral of the story, to answer your question right now, these anonymous functions, closures, I guess you could think about it as, they capture variables in their environment. So the counter referenced in this Go routine on line 9 is the same memory address. If you actually printed out the memory address, it would be the same as the one on line 6. So it's not like counter is being copied and then mutated separately in this function. We've actually captured the original counter value, and all 1,000 Go routines are going to be incrementing the same counter value. Does that answer your question?
Yeah, so they're doing it in parallel.
Mm-hmm.
So how do they...
So is there a problem there? Is that kind of what you're thinking?
Yeah.
Yes, there's 100% a problem there. And I want to spend some time on that problem in a second. But just put a pin in that one, because there's something else I want to get to before we jump to that. But that is an excellent observation, and I'm glad you caught it. Okay, so let's first, before we move to that problem that Murcha just brought up for us, let's fix the problem of the main program doesn't wait for all the Go routines to finish. So Go, the standard library, gives us a primitive that allows us to spin up a bunch of Go routines, wait for them to finish, and then we can basically continue our execution. And that's called a wait group. So this is in the sync package. Most of the, I think almost all of the sync primitives that I'm aware of are in the sync package. Let me just open that up real quick. And we'll look at what the API is for that. Okay, in the sync package, there's a bunch of stuff. The one I want to look at here is wait group. So the way that this works, in fact, it probably says it here. Yeah, the main Go routine calls waitGroup.add to set the number of Go routines to wait for. Then each of the Go routines calls waitGroup.done when finished. At the same time, waitGroup.wait can be used to block until all the Go routines have finished. So that's what the API is. Let's actually look at how we would use that in this case. So I'm going to go ahead and create a new wait group right here. And what basically you could think about this as a big counter that allows us to wait for the counter to return to 0 after it's been initially incremented. So in our case, we want to increment 1 for every Go routine we spin up. So we'll do waitGroup.add 1, and then when our Go routine is done, we'll do waitGroup.done to indicate that this Go routine is done, and that will effectively decrement the counter. And when that counter, that wait group counter, I shouldn't say counter because we have a variable called counter. When that wait group returns to 0, then waitGroup.wait will be allowed to proceed. In other words, this whole program will block on line 15 until all 1,000 Go routines have called waitGroup.done. Any questions on that? Okay, this is probably a good time to introduce one other concept that we just haven't had time to get to, and that is the defer keyword. The defer keyword allows you, it's kind of like the go keyword in that the next argument needs to be a function call. But what defer does is it says, I'm going to run the function that you give me, but immediately after this function returns. And the reason that this is nice is, let's say that, well, in this case, I need to call waitGroup.done when this go routine is done, regardless of what happens in this go routine. But let's say there was like some if error checks and then a return, and maybe there's like 3 error checks. I don't want to have to do waitGroup.done here, waitGroup.done here, waitGroup.done here. That's very redundant. And so what Go allows you to do is you can use the defer keyword, and we're effectively saying, hey, regardless of what the actual control flow is of this function that we're in, just make sure that after the return is called, you call this function as well. And so what you'll often see, especially for wait groups, is right at the top of the Go routine, we'll just defer a done so we don't forget it, and that there's no path, no control flow path where waitGroup.done does not get called. That's what the defer keyword does. It's useful for other things. We'll look at a few other examples later today. Okay. Any question on the wait group? Let's go ahead and run it. My auto importer is apparently not working today. Okay. Now, interesting problem. We thought we were kind of on the right track, but we're still getting not 1,000. So this leads us to kind of another concept that we need to be aware of, the one that Mircea beautifully alluded to a minute ago when we're dealing with concurrency. So when I was first learning about Go, this concept was surprising to me, and I'm glad that Mircea was so smart and keen on finding it. I didn't quite understand why this counter plus plus, how this counter plus plus could be messed up. And this is what we would call a race condition, where 2 threads, 2 Go routines in our case, but ultimately it's because 2 OS threads are trying to operate on the same memory at the same time. And that's very possible for even counter plus plus. Like, this is not one operation. In fact, let me see if I can pull up. Yeah, here's a good example. This operation is actually not one operation. If you look, I ported the same thing over to C. And if you actually look at counter plus plus and C and the assembly it produces, what your CPU is actually going to do, it does 3 different operations. It moves the counter value from memory into a CPU register. It adds 1 to it, then it moves it back into memory. And so this one operation that we see in Go is actually 3 operations when your CPU is executing it. And because it's 3 operations, it's very possible for 2 threads to try and execute those same 3 operations and interleave them at the same time. And so what that actually results in, let's see if I have a diagram for that. Yeah, here we go. What that actually results in, these are the 3 steps essentially that your CPU is going to do. I've illustrated Go routine 1 and Go routine 2 right here, and the reads and the writes that they'll each do. What's effectively happening that Mircea was alluding to is that Go routine 1 reads right here. It reads the number 1. Then Go routine 2 comes along and it also reads the number 1, right? Because we haven't actually Go routine 1 hasn't incremented it yet. So Go routine 2 reads the 1. Now we're back to Go routine 1, who finally says, all right, 1 plus 1 equals 2. I'm going to write that back into memory. And M2 is doing the exact same thing. It's like, okay, I read a 1, now I'm going to add 1 to it. Now it's 2. And the result of 2 separate read-write operations that got interleaved is 2 when it should have been 3. Does the problem make sense before we talk about how to solve it?
It does, yeah.
Okay. So what would be ideal is if we could do something like database transactions, right? We probably all worked with database transactions before, where you can say, I want to do a series of operations, but I don't want anything else to like get in the middle and mess up what I'm doing to read a half committed change or something like that. Essentially, we want to say, I want to put a boundary around the read and the write of both of these so that they happen atomically. And there is a way to do that in Go, and it's called a mutex. A couple different flavors of mutexes that we'll look at maybe if we have time. But the idea behind a mutex is we want to make sure that the read-write happens all at once and that a different read-write can't start until we're done with ours. So the API that Go gives us to do this on the mutex is that when we begin an operation, right? When we begin an operation right here, we want to be able to call something called lock. We want to take a lock. And when we're done with the operation, we want to call unlock. And I'll show you what this looks like in code in a second. And then we do the same thing here, lock and unlock. And well, actually, let me show you one other thing. What this effectively does is if you could kind of like visualize this like a funnel where, you know, you got a bunch of Go routines working on their own stuff up here like this. And then once you get into this mutex, the lock and unlock, you have to go through this section, which we call the critical section, one at a time, because the lock called by Go routine 2 right here, right? The second one that wants to do it, that's going to block and sit there and wait until the previous Go routine unlocks it. You can't have two Go routines take a lock at the same time. They have to do it in turns. And so that's why I think a funnel is kind of a good way to visualize it. Once the act of taking the lock and releasing the lock gives you a sort of funnel point where all the Go routines kind of have to coordinate sequentially. Let's look at what this might look like. So sync package also has a mutex. And my auto completions aren't even working. And it has, that mutex has two methods on it, lock and unlock. We'll call those just like this. And the code that occurs between the lock and the unlock is what we call the critical section, this one here. And this will execute sequentially with all other threads and Go routines. And now we get to our 1,000. Any questions about that?
Just real quick, you are on the iPad share still.
Oh, shoot. Thank you. Yeah, there we go.
But it looked great.
Yeah, in your head. Just imagine what I'm telling you. Yeah, so here's what we did. I created the mutex up at the top under my wait group, and then I took the lock here, mutex.lock, and I unlocked it when I was done, and the part between that was the critical section I was talking about. Any questions there?
So you're saying that assuming that the Go routine would do something a little more complicated than just like incrementing a counter, everything that doesn't have to do with objects from outside the context would be not wrapped between lock and unlock, and you would only wrap the actions that touch on objects that are outside the context of the Go routine. So on line 16, you could be doing a bunch of local logic to the Go routine, but then just to make sure that you avoid a race condition, you wrap any outside connection in the sense of the context between lock and unlock. Is that?
Yeah. So if I'm understanding you correctly, you're saying is the critical section really just data from outside the scope of my Go routine that I am wanting to modify. Is that effectively what you're saying?
Yes.
Like if I had some other data in here, you know, D equals whatever, I don't need to lock that because I'm the only one that owns it. Is that basically what you're saying? Yeah, that's essentially the principle. And if I were to kind of reduce it down to like something to keep in the back of your head, it's no unsynchronized writes to shared memory. And the distinction writes versus reads is important because if we weren't modifying this counter, but we were just like printing it out, we wouldn't need to lock that. We can look, we can have as many threads as we want looking at the same memory as much as we want. The problem comes when you have at least one party in this pool of people looking at the same memory. The problem is if you have one party that's changing it. That's when you need to be thinking about locks, because now you don't really know if the value you're seeing is actually the value that it is. And there's some really interesting problems when your value like takes up large amounts of memory where maybe part of the memory got updated and part of it didn't. And then you actually get legitimate memory corruption. Maps are an interesting example of that. The Go code will actually panic. It will crash your program intentionally if it detects that you are reading a map and modifying it at the same time from two different threads. And I imagine that's because there's a lot of different data structures under the hood of a map, and all of those need to happen atomically. Otherwise, you could have like memory corruption issues reading a map without looking at, you know, the correct state of it. So moral of the story, yes, Murcha, you're exactly right. And the one distinction I would make is that it's the writes that really matter. If all you're ever doing is reading, then you don't need to worry about locks.
Maybe you can clarify something for me. So the wait group creates, when we do the add, a single thread?
Yeah, good question.
Create 1,000, because if I look at the iteration, right, we go for I, so it's 1,000, add 1, but then immediately hand off everything else. So is it one wait group we added before it hands off everything, or is it 1,000?
Yeah, could you, sorry, my internet cut out for 1 second. Can you repeat the question one more time for me? I apologize.
Yeah, so right when we step in, let's say the first iteration through the for loop,
okay,
we add one wait group, and then the next step, we hand everything off. So is that just one wait group we're using? Or because it's in the for loop, it's 1,000, but we're handing it off? 1,000 wait groups or one before the handoff, I guess I'm a little lost there.
Yeah, let's see if we can, let me walk through what the program is actually going to do. I'll get rid of the mutex stuff just to make this a little cleaner. Okay, so this is kind of just the wait group example. So what's happening? I'm going to add a comment up here that's like the wait group counter. So I'm going to put the counter that's in the wait group. And here's the thing to kind of take away. When this counter will be incremented at least once. When it goes back to 0, this wait function down here will unblock. If this is anything other than 0, if it's like 1, this will never return. And so we need a way to get this back down to 0 if it goes up. And remember that the objective here is to start a bunch of Go routines and wait till they all finish. That's what we're trying to accomplish. So here's how it works. First iteration of the loop, I is equal to 1, or well, I is equal to 0. That's the first iteration of the loop. The wait group counter now goes to 1. Second, and we've started one Go routine. Second iteration of the loop, which is I, whatever, we add to the wait group becomes 2. So you can kind of see the pattern here. Every iteration increments the wait group, and this number just keeps climbing and climbing and climbing as we start more Go routines. But as the Go routines start finishing, as denoted by calling wait group.done, that's the only way the wait group knows that a Go routine finishes. When wait group.done is called, then we start decrementing again. And as each Go routine finishes, the wait group starts working back down towards 0. And once we've essentially the wait group goes all the way up to 1,000, goes all the way back down to 0. Once it goes back down to 0, we'll be able to proceed past line 18 because it will no longer block. Remember that this main thread actually only is executing this code. This is the only code that it executes. This go routine gets executed some other time. So we're going to blow through. We're going to blow through this, and then we're going to sit and wait here until that wait group drops to 0. Sorry, that was long. Did that answer your question?
No, that definitely helps, because I was stuck in here's the iteration, and then the go routine takes off, but we still iterate through the wait groups because it's the for loop regardless.
Yeah.
That part doesn't go away because of the go function. Okay. I'm caught up, and thanks for dealing with me.
No, that was an excellent question. So I'm glad we covered that. Okay, so there's another way to solve this problem that's useful sometimes, and that is using atomics. So atomics are some primitives that Go gives us. Let's see if I can pull it up here. Where are you? Yeah, in the sync package, there's another package underneath it called atomics. And what you'll see is there's a bunch of types: atomic bool, atomic int32, atomic int64, and so on and so forth. Basically, a bunch of primitive types that are considered to be atomic. What that means is that they'll give you methods like, let's look at the int32, like add or load or compare and swap. And what it means, like the reason we call them atomics is you could kind of pretend that this incrementation that happens inside the add method is guarded by a mutex. Now it's not, but you could kind of imagine it as being a replacement for a mutex, such that each one of these methods will happen in a sequential way that will guarantee that the result is what you would expect it to be, despite other threads trying to do the exact same operation you're doing, or trying to modify the same number. So if we do atomic int32, and I will need to, there we go. And then we use the counter add method like this. And then when we're done with it, we use the counter load method. This would be another way to solve the problem. Now you don't have to use mutexes. But in reality, the reason you use mutexes is because most data structures aren't a simple counter, right? Most data structures have a couple different fields. Maybe a change needs to update a couple different things, right? And you need that entire process to be transactional. And so you can use the mutex and the fact that it gives you a critical section to do whatever you want inside of that critical section. So I would say that I don't use these too much, but they are helpful if you're just dealing with numbers and stuff. Okay, one last way to solve this that I hope will drive home the scheduler concept is, let's go back to what we had before. So this, man, just restart VS Code. Yeah, so this was our problem before, right? We couldn't get the, even though we were waiting for all the Go routines to do the incrementation, it wasn't working because there's a race condition. These Go routines are clobbering each other and we're missing key updates. One of the ways to solve this is just to say, hey, you can use these virtual threads, these Go routines, but scheduler, only schedule them onto one OS thread. And this, I'm not familiar enough in Python to claim that this is what Python does, but I believe that this is one of the things that Python does is it will confine the execution down to a single OS thread at one time. Mircea, can you check me on that? Have I just spouted something untrue?
So the thing with Python is you would actually spawn multiple processes. It doesn't really work in the same way. And then things have changed recently in a way that I haven't studied enough to where I can be authoritative. So
fair enough. Yeah, fair enough. So maybe I shouldn't have made that comparison without also having studied that completely enough. But moral of the story, one way to solve this problem is just to make it impossible to, you can see how dependent I am on that auto importer, is to make it impossible for multiple OS threads to clobber the value. And so now we've actually solved the problem, right? We can increment this counter for multiple threads because the Go runtime is just saying, I've got 1,000 virtual threads to map onto one OS thread. And the reality is that only one virtual thread will physically be executing on the CPU at a given time because we've limited it to one. But as soon as that's anything other than one, then you have the possibility of those values clobbering themselves. And it gets higher as the number of processes actually go up. Interestingly, 2 didn't quite trigger it, but 8 did. Okay. Let's see, is there anything else I wanted to cover on that? Any last questions on kind of the concepts we've explored here? Okay. Let's move on to something that might be helpful if you are working on or wanting to do the weather project. So we had looked at a basic API server last or 2 weeks ago. I'm gonna go ahead and pull that code up real quick. Okay, it looked something like this. This is what I had sent in the Slack and what we'd kind of ended our HTTP server discussion on. I'm going to do a couple of things. I'm just going to change back to kind of the first example that we looked at. Doesn't have any fancy routing or anything. It's just a basic HTTP server. I want to show how we can use Go routines to accomplish one of the goals of that weather API project was to cache something and then delete the cache after a period of time. And I'll work through that example with you. We won't do the weather example, but we'll do a different example so you can kind of see how it might look. Okay, so I'm just going to make sure that this works. Hello. Make sure that we've got everything up and running. Yes, okay. API server is running. If we curl it, we get our hello back. Okay, so this is a basic API server. If we wanted to add some state to this, let's say that we wanted to be able to send in our name and get like a score, maybe the number of times that you made a request within a certain period of time. Maybe we say, how many times can you make a request within 1 second? Let's implement that sort of API in here and just see how Go routines, concurrency, etc. might come into play. So I'll create a map of scores that will map the names that we send in to a score, which would just be a counter. And then whenever we make an HTTP request, let's go ahead and grab out the name. Okay, man, this missing syntax highlighting is gonna kill me. I believe it's url.query.get maybe. Yeah, I think it's that. So we'll pull a name out of the query, nothing fancy here, and then we'll store it in our scores. We'll say score, we'll increment the scores, and then we'll return the current score. And we'll write that out. There we go. Now my imports are working. Okay, so print out the name and the score. Now let's go ahead and run this and see kind of what we're dealing with here. I'll run it in my browser. Now, one of the problems is I need to initialize my map. Otherwise, there's a panic. So I'm going to go ahead and do that. My syntax, all right. Sorry for the setup. I promise this will be worth it in the end. Okay, So this is printing out my name, which I put in the query parameters, and my score. I'm just hitting refresh over and over. So it's a stateful API server with a counter. Now we could actually use a go routine to reset this counter after a period of time. So what I might want to do is check and see if there is a score for this person. And if there's not, maybe I want to start a timer that will reset the score. So I can, we had talked about when we originally talked about maps that maps will give you back two values if you ask for them. It will give you back the value at the key in the map, and then it will also give you a value indicating whether that key even existed. So we could say, hey, if it doesn't exist, this must be like the first request. So I'm going to go ahead and start up a go routine right now that maybe waits for like a second. And then once it's done, let's go ahead and delete the score for this person. Like this. Go ahead and run that. Now, if I hit it, you can see that I'll get up to like 9 or whatever, and then it will reset back to 0. So this go routine, the first time basically on my first request, this go routine starts, waits for 1 second, and then deletes the score. Now this there's some problems with this. Again, the problem that Mircea brought up is we're modifying scores, the scores map, and reading it at effectively the same time. It's not exactly the same time, but it could be. And so there's a potential for a race condition here. And since we're dealing with maps, it could be a crash. And so we should be using a mutex for this. And so often what you will see in code is people will have maybe their data on the struct, in this case, it's our scores map, and then they'll have maybe like a mutex. I like to use mu. They'll have a mutex that's specifically designed to guard that particular property. And every time they read it, they will take the lock, s.score mu, and every time they are done with it, they'll unlock. And we'll just defer unlock right now. This is another case where defer is nice. If you don't unlock, your program will just sit there and wait forever. And so it's often good practice to defer your unlock right after your lock so that someone who's reading the code can know, all right, this lock is never held for too long. But we have to do the exact same thing in our go routine, right? Because our go routine will is modifying that scores map. And so when we do this, it also needs to take that lock as well. One other note, I don't want to do this. I want to do the sleep before, not after. Otherwise, I'm going to take the lock for a whole second while I'm waiting for the delete, and then unlock it at the end. So this is something you should be aware of, that you want your critical section to be as small as humanly possible, not necessarily in code, but in the amount of time that the lock is actually going to be held. So I'm going to wait until after the sleep to actually take this lock. Okay, so now we're going to see the exact same thing. We've just made it thread safe now, so there's no worry of the problem that Mircea brought up with the counter. Any questions? I kind of blazed through that without taking any questions. So let's, any ideas? Okay. I'm going to throw this in the Slack, and then we're going to move on to a new concurrency topic. Okay, I'll get rid of all of this. All right. I've lost my iPad here. Hang on. Okay. In most cases, you can't just start a go routine and then forget about it. In most cases, you actually want to start a go routine, do some work, and then get the result of that work back so that you can use it somewhere else. Maybe some examples. There are some examples of both cases that I can think of. Concrete example of maybe what we've looked at so far, where you just kind of fire and forget on the go routine. A concrete example of that would be how the Go HTTP server works. It gets a TCP connection, starts a Go routine to handle that and any HTTP requests you make, and then it just forgets about it. Like, it doesn't even care what happens after that point. But there are other cases where I'm thinking about maybe our weather API project, for example, where you want to maybe make HTTP requests to, you know, for the current weather from 10 different zip codes, for example. And you could do that sequentially, but it would be really nice. It'd be a lot faster if you could make all 10 of those at the exact same time. And in that case, you actually want to get those weather results back. You can't fire and forget. You just want to fire and then collect everything back later. So the question is, how do we communicate between the Go routine that we started that's doing work in the background while we're either waiting for it or doing something else? How do we communicate between that and the main Go routine? And the answer is channels. And channels have, you may remember back from kind of our original discussion that we talked that channels were one of the composite types. You can create a type of channel, and these channels allow you to do, shoot, where was I? Yeah, here we go. They allow you to do, they kind of have two big goals. Communication, that's kind of what I'm talking about right now. How do we send data back and forth between Go routines? But they also have another really important attribute, and that is synchronization. And I'm hoping we can, you know, have enough time to explore both of those features of channels. So let's talk about, well, let's see, what's the best? I'm trying to decide if we should talk theory or just look at the code. Let's talk theory for 1 second. Channels basically are a first in, first out queue that is thread safe. And what I mean by that is it's a queue that you can send messages to that get received by anyone, but usually another thread. What usually happens is you'll have thread number 1 write a message to a channel, and then thread number 2 can receive that message. Let's see if we can look at maybe some examples of how that works in Go. Channels are created using the make keyword. Now, you might remember we could use the make keyword to create slices of like specific lengths and capacities. We do the same thing for channels, except instead of, you know, using the slice type, we use channel, and then whatever the type of message that we're going to be sending on that channel will be. So let's use int for now. We'll say that this channel can only send integers back and forth. You can use structs, you can send slices back and forth. You can even send channels of channels if you really wanted to. So any type can go here. You send functions for that matter if you wanted to, any type. So let's explore how this might be used. So I could reference this channel from my Go routine and say, I want to send the value 10 on it. And then on the main, in the main function, I can actually receive that value like this. Now the arrows are kind of funky. So what are they saying? Main thing to keep in mind is that the arrows always point left and they indicate the flow of data. So in this case where I have 10 arrow C, I'm saying that I'm sending the value 10 onto the channel C. Then down here, it's kind of reversed, right? The C is on the other side because I'm receiving the value and assigning it to a new variable V, but that value was obtained from the channel C. And if we go ahead and run this, we should just get our value 10 out. Okay, so that's creating, reading, and writing to a channel. Any questions about that before we move on? Okay, channels by default, there are kind of two flavors of channels. There are buffer channels and unbuffered channels. We're going to talk about unbuffered channels first. If I were to try and do something like this, so I've just gotten rid of the Go routine and I'm just trying to send a value on the channel and then receive a value on the channel. If I go ahead and try and run this, my program will crash. It will have what's called a deadlock. A deadlock is when Go observes that all of your Go routines, in this case we only have one, it's the main function. It observes when all of your Go routines are waiting on each other, essentially. They're waiting on a condition that will never occur. So what exactly is happening? Well, the stack trace points us to the line where the problem is. So if I click on it, it says, hey, it's line 10. So our program is getting to line 10 and it's crashing because it can't proceed past line 10. So why is that happening? And the answer is that this channel, this first in, first out queue, has a capacity of 0 right now. It's what we call unbuffered. That means that the sending will block until a receiver is ready. This is where the idea of synchronization comes into play. It acts as like a point where Go routines have to come together to exchange a value. I think a good analogy of this is it's like having a package that requires a signature delivered to your house, right? The package can't be delivered unless both the delivery man and you as the recipient are there at the door to make the exchange and sign for the package. That's what an unbuffered channel is. And as you can see, our problem is that as of line 10, there's no recipient on the other end of the channel. That happens on line 11, right? And so it's trying to send to a channel. It's trying to make the delivery to a package and nobody's home is essentially what's happening, just to continue the analogy. If we were to make this channel buffered, which basically means the first in, first out queue now has some space to store values itself. It's not just the middleman now, it can actually hold them. The analogy that I think is probably best for this is that it's a mailbox. A buffered channel is a mailbox where the USPS person, or I guess we have some Romanian people, so USPS probably doesn't mean much. We have the mailman who brings the letter and leaves it in the box, and then I, as the recipient, can come and pick that letter up at any time. We don't need to synchronize. We don't need to meet up. It can happen anytime. That's what a buffered channel is. And you can specify kind of the size of that buffer, how it's called the channel's capacity, how big that capacity should be. How many values am I allowed to put on this channel without there being a corresponding recipient and not have it block? And so if we run it now, it works just fine. If we try and send a second value without there being a recipient, we get the deadlock again. And if you actually look at the stack trace, it's saying it blocked on 11. So it sent the first one successfully because there was space in the channel. The second one did not succeed because the channel was full and there was no recipient. The recipient doesn't happen until 12. All right, we'll take a break there. Any questions about those concepts? Okay. It is very rare that you'll see a case like this, where we have a channel. I mean, I can't even think of a good real world case off the top of my head where I'm going to make a channel and like send and receive values from it in the same Go routine, like in the same, not across threads, but within the same one. So usually channels are helpful mainly for this reason, where I want to have a way for two Go routines to talk to each other. Okay, a couple other things about channels. Let's do something here. If I go and create a channel of two values, so we'll do like maybe 10 and 20. And channels, they can be used in a couple of different ways. We just saw how you could receive values directly from them, but that's not the only way that you can consume values from channels. Sometimes you don't know how many values are on the channel, and so it's helpful to be able to just loop over anything that comes over the channel. And so the for loop, the for range loop that we've looked at for iterating over slices or iterating over maps, you can also use to iterate over the values of channels. So we'll move our print up just like that. And we can iterate over each one of the values that comes through this channel. Now I've made the channel capacity of 2. That allows me to send 2 values without blocking. The other thing I could do is go like this, send them in a Go routine, and then I wouldn't have to have any channel capacity, right? Because this Go routine, I'll start reading values off the channel while this Go routine is sending them in the first place. So these are 2 essentially equivalent ways of solving the problem where the channel blocks. Let's go ahead and run this. Okay, so we get the deadlock again. Why do we get the deadlock again? And in fact, it says that we got the deadlock on line 16. We got it on the for loop. And the answer is, how do we know when the channel is done sending messages? How does the for loop know that there are no more values that will be sent on C? Especially, how does it know that when there's a totally separate thread running at a totally different time somewhere else that's producing those values? And the answer is that channels can be closed. So I can come in here and use the close keyword to send 10, send 20, and then close the channel. And the for range loop uses this close to understand when it should stop waiting for new values. When it sees the close, it exits the loop. And so you'll see when we run this, it runs just fine, our program works just fine because the range sees the close, and then we're able to move on with the program. It's not just stuck waiting. A couple of things about close. You don't need to close a channel. It's more of a signaling mechanism. So if you have a channel that you put a bunch of data in and then you never use it again, the garbage collector will actually go in and will clear it up. You don't need to explicitly close it. So not every time I create a channel do I also use a close. I only use it in cases where I need to signal that there are going to be no more values on this channel. And only some problems require that. This is one of them where I'm looping over the channel. I need to signal that close. Another thing about close, who should close it, right? Could I put the close right here? Like, well, heck, could I put it right here? The answer is no, because I need the for loop to see the close. So it's got to be before the for loop, but could I put it outside of the go routine? And the answer is, interestingly, what's happening here is that the channel's closed, the for loop returns, and the program exits before we ever sent any value. Here's kind of an interesting thing about closing that I meant to illustrate that I did poorly in that example. If you try and send on a channel after it's closed, your program will crash. And so to answer the question, who should close the channel? It should always be the sender. You never want the receiver to be the one that closes the channel, because if the sender doesn't know, it might try and send a value on that channel and it will crash. So moral of the story, use close. The sender should use close to signal to the receiver that there are no more values in cases where the receiver might care about knowing that there are no more values, i.e. this for loop is a good example of that. Let's look at one other example here. We'll send 10, 20, and then close C. And then I'm actually going to read the values off this channel here and print them out. Now, I did something a little different here, right? I was doing this before. I've added a second parameter. When you receive a value from a channel, the channel will give you two things if you want them, or just one. By default, it will always give you the value that you're asking for from the channel. The second thing it will give you, if you care, is whether the channel is closed or not. And so we can actually see what happens when you receive on a closed channel. If I print this out, do it at the top here, you can see we got 10 true, that the channel's okay, that it's not closed. 20 true, 0 false. We got the 0 value of the channel, which is integer 0, and then we got a Boolean indicating that the channel has now been closed. And this is another interesting thing to point out about channels. When you close a channel, it does not mean like, hey, we're done, everybody stop where you are. It is not actually saying that. Closing a channel just means that, hey, when the channel is empty, when all the values are received from it, you can't use the channel anymore. You can't send on it, and you're not going to get anything when you receive on it, anything of value. Because to illustrate that, what you can see here is we're actually sending a value, and closing it, yet we're able to receive a value, and then we see that it's closed. So that close doesn't take effect immediately. You can almost think about it as like the last value in the queue that indicates that, hey, this is it, no more. Any questions on that? All right. Let's go ahead and let's look at another example of how to use channels. So we've talked about the for loop, talked about plain old sending and receiving. Now I want to talk about the select. And the select is very powerful. Let's illustrate this by creating a channel of integers. And we'll create a go routine that will send values, incrementing values like 0 to 100 on this channel, like this. And we just want to sit and receive values off of this channel. And maybe, you know what, I'll send like every second. Timed out second. There we go. Now, if I were to do something like this, receive from the channel and then print it out, we would probably see, yep, every second we get one value, and it's going to do that up until we get to 100. And then, in fact, we're not even closing the channel, so we'll just sit here and like this is not a good program. What if I wanted instead to say, hey, read values out from this go routine, but only for like 10 seconds or something? I could use, and this is not a super practical example, but I want to illustrate what a select actually does. So I'll wait for 10 seconds in this go routine. And then and I'm going to create a second channel. I'm going to call this one quit, actually, because when we close this channel, it can be a channel of ints, doesn't really matter. When we close this channel, I actually want to abort the process. And then we'll close quit. Now, one of the problems is, okay, when we're in a for loop and we're sitting here waiting for this channel, how would I know that something had come back from the quit, right? This is blocking. And in fact, if you just run it, this program will crash because, well, actually it will wait for 10 seconds and then it will quit. This does not do what we want it to do. So the question is, how do we wait for two values at the exact same time from two different go routines? And this is what the select is for. The select lets you provide a list of cases that it will then evaluate and take whichever one is ready. So when you're trying to do channel sends or receives in a select statement, it will go with whatever case becomes ready first. If we were to do, basically put what we had below here and print out, V. And then we were also to say, hey, wait for a value on quit. And I'm not putting it in a variable because I don't care what, I'm just waiting for the close. Then what we could do is print out that the program had exited or, quit, something like that. Get rid of these. And we'll go ahead and run that. Maybe I shouldn't have waited for 10 seconds. Maybe I should have waited for 3 or something. So the idea is we're going to loop over and evaluate these cases every time right up until we get a message on this channel. And then because this channel is now ready and this one is still waiting, a second for this value to be sent on it, then this case then becomes evaluated and we return which exits the program. So select lets you wait on multiple different go routines, multiple different channels from possibly multiple different go routines and pick whichever one is first. In our case, we loop over that so that we can do it over and over and over. Any questions about that?
Maybe just a quick one. If
Yep.
if the first case we made was shorter, it would then everything would have been listed and be false, so it'd immediately go to the quit channel and be done then, right?
Let's see. If which thing was shorter?
If channel C, if everything was consumed, and in the case statement, since it's consumed, it wouldn't be valid, it'd be false. So it'd go to case quit, correct?
I see what you're saying. So if we got rid of this so that we sent a bunch of values immediately, And so all of the values were sent. What would
Yeah.
happen if there was no more to be sent on this case? Is that what you're asking?
Yeah, my assumption is, well, a case is not case closed, but it's false, so it goes to quit then, is my
Yeah,
assumption.
good question. Let's run it and see. You're close. You're super close. Notice that the program hasn't returned. Now it's returned after 3 seconds. So what actually is happening is this case, like you said, gets evaluated 100 times really quickly. We print out all the values. It doesn't mean that just because this is false doesn't mean we automatically fall through into this case. This condition still needs to be met for this for the body of this case statement to actually be evaluated. And that's why the program does this over and over and over and then just hangs for 3 seconds because we're waiting for this quit message, which gets sent after 3 seconds to actually be sent. So moral of the story, you don't automatically drop into cases. The condition of the case will have to be met for you to drop into that case.
Got it. Thank you.
Yeah, good question. Any other questions? Okay. You can actually piggyback on this select syntax to do a couple of different things. So if I created a channel that had the capacity for one value and I wanted to try and send something on it, but so like before we saw something kind of like this, where one of these would succeed and the other one would fail, right? Because the channel doesn't have enough capacity. Get rid of that, then it works. Oh, I didn't save. There we go. Then it works fine. So you can also use the selects to prevent a program from blocking and instead just proceed. So it's like a best effort type of send on a channel, if you will. The way you do that is with, let me comment this out. So this is our blocking send. This is our non-blocking send. I misspelled that. Oh well. So we can go try and send in a case. So before we were actually looking at receiving in a case statement, but I can use the same syntax to send in a case statement. And effectively what happens is the select is just going to work down the cases and see which one is not blocking. Now, if I had a default case to this and we get to here and this send fails, this send, it's not going to fail. This send blocks, then we'll just move on to the default case, which is nothing, and proceed. So if I run this like twice, and then I print out the values that I get, maybe we close C, range over it, and print out what we get. We should see just the 10. There you go. So this one worked, right? Because our channel had capacity of 1. This one did not work, but it didn't block. It didn't crash our program because we used the select statement to do a non-blocking send. Just proceeded with the default case. Does that make sense?
It does, yeah.
Okay. You can also do the exact same thing with a receive. So say that I had like this. I'll get rid of this now. We've sent one value. If I were to try and read without the select statement a second time, which I'm doing here, the program would not let me do that. It would deadlock. But because I'm doing a non-blocking receive, it works just fine. And here would be your blocking receive. That's going to crash your program. Okay, so that's kind of the power of the select. We are almost out of time. Wondering if we can make it through the real practical example of this, or if we need to. All right, here's what I'm going to do. I'm going to copy some code, and then we'll do the concurrency part, and then we'll be done. So last week or 2 weeks ago, we talked about HTTP requests and responses, and we had written out this struct, which we were using to pull data from the HTTP bin, like public server. So we go to HTTP bin, get some JSON data, deserialize it into this, and then we can use it. The example I want to go through, I want to kind of put some practical examples to why the concurrency is powerful is, let's say we wanted to make a bunch of these HTTP requests at the exact same time, rather than just sequentially. I want to make 10. I don't want to do it one after the other where I'm waiting 10 seconds for 1 second a piece. I want to actually be working on multiple at the same time. Okay, so the way that I'll do this, and I'm going to go through it quick, interrupt if you want, but I'll leave some time at the end for some questions. I'm going to go ahead and create our for loop. We're going to iterate 10 times, creating a Go routine that calls this get data function. Let's see. Yep, just like that. It calls this get data function. So we're going to make basically 10 calls immediately at the same time. Now, as we already learned, we need to use a wait group because we don't want the program to exit until all our work is done. So I'll throw a wait group in there, and I'll do wait group.add, one for each iteration of the loop, and then done when the Go routines are finished. Now, I have an error, and I have some data that I want to do something with, right? Maybe the first error I want to crash my program, right? I don't care about trying to just keep going with the other 9 if one fails. I want to crash my program. And for the response data, maybe I want my main Go routine to handle the data after all of the other Go routines, the 10, go and get it. In other words, I want this to do the I/O work. I want Go to do the I/O work in the Go routine, and I want to do my compute work back here in the main thread. So how do we do that? Well, with channels, what we'll do, or what we could do, is we could create a channel for each thing, for our data and for the errors. So I'll create a channel of responses, and I'll create a channel of errors. You can see I can use my own custom structs for those channels. It's no problem. Then when we get down here, I'll just send my errors on this error channel in return, or I'll send my data to the data channel like that. And maybe what I'll do is I'll throw some logging in here. Let's see. Yeah, something like that. Okay, that's just to help us kind of visualize what's going on. Now, that's going to go ahead and do its work. I need to come back and wait for all this data to come on the channel. So I might say, and the other thing that I want to take into consideration is that there are some errors as well. So I'm going to use our select construct that we just learned about to switch between the two. So when I say switch between the two, I mean handle whichever one comes. So I'll do, if I get some data back, I want to deal with that. If I get an error back though, from the error channel, I'm just going to crash the program for simplicity right now. For the data, I'll throw it into maybe a slice of my struct. Like this, and I'll put the data into it in the main Go routine. Okay, the last thing that we're really missing is how do we know when there will be no more data on this channel? Because right now this is going to loop indefinitely. It'll get the 10 values and then we don't know when it's finished. So we learned about the close call for that, but when do we close it, right? One of the rules for close that we talked about was the sender should always be the one closing. But what if you have 10 senders, which is exactly what we have in this case? You can't close the channel 10 times. And how would you even know from one of the Go routines that it was safe to close without talking with the other Go routines? And the answer is we can use the wait group for that. We can use the wait group to tell us when all of the Go routines are safe to, or when all the Go routines have done their work and are safe to send. Sorry, when the channels are safe to close. Now, this is interesting. This will actually crash our program, and I'll show you why. it didn't crash our program. It just blocked our program indefinitely. All of these Go routines are making their requests and they are trying to send on the channels, but the channels have 0 buffer capacity. So this wait, basically the Go routine is never finishing because it's sitting here waiting to send its data. And we never make it past line 45. We never close our channels. We never read it out. So the simple solution for me is just to run this in a separate Go routine as well. So essentially we have 10 Go routines producing values. We have 1 Go routine watching for the 10 to finish, and then it closes the channels. And in fact, I don't even care about closing the air channel. I just want to signal that the data channel is closed. And then over here, I'm going to accept that second parameter. And I'll say, hey, if the channel gets closed, return, exit the program, and maybe log out, got values with the data that we got. Now let's go ahead and log this out, and we'll hopefully have completed kind of a slightly more practical example of how concurrency can be used in practice to solve a problem. Now you can see that these came out of order, but they all came very quickly. And so instead of doing it sequentially, we got the benefit of speed by using concurrency. Sorry, we're basically at time, but any questions to end our whole discussion about concurrency?
No, just the fact that you got that much in that amount of time. Pretty great. Thanks for doing this. I think it's a lot clearer for me now.
Cool. Well, happy to hear that. There are, I mean, as you probably saw, like not having this thing in here, the program just crashes. There are some very big, I don't want to say foot guns, but basically foot guns when you start using concurrency. But the rules that we've talked about, like synchronized writes should always be synchronized, and senders should always be the one to close the channel, and channels block unless they're receivers. Keep those rules in mind, and they will help you avoid kind of the pitfalls. And I will say, just my own personal opinion is that while there are some challenges with concurrency, it's a different way of thinking about programming this or solving this problem. While there are some challenges there, this Go makes it like easier than any other language I've done asynchronous programming in, is my personal opinion. And so as you learn the rules, you'll see that it becomes very easy, very natural over time as well. All right, if there are no other questions, feel free to drop. Thanks, guys. Sorry we rushed through a ton of stuff, but glad that we got through what we did.
Hey, thanks, Clark.
Yeah, you bet.
Thanks, Clark. Appreciate it.
Thanks, man.
Yep. Hey,
Have a great weekend. Bye.
thank you. You too.
Bye-bye.